I hope you can all hear me now. Please, can you hear me now?
Yes, sir.
Good. Oga called, so I have to just speak. And I've been using my distance for this. Sorry, please. So we are talking about the activated complex. Let me just go back a little bit. The activated complex is a certain height where the chemical reaction must attain before products can be formed. That height is what we call the activated complex. In other words, we can say that when the colliding molecules acquire the activation energy, which is the minimum amount of energy that is required, when they get that activation energy, the reactant molecules form something called a complex molecule. They form a complex molecule. Now, when they form a complex molecule, it helps them possess high energy. Now, when they possess this high energy, the high energy transitional state, this high energy transitional state, that reactant must attain in order to form a product is called the activated distance. That's high energy they attain in order to form a product is what we call the activated complex. And so the high energy state, which comes as a result of the colliding between the molecules, and when they collide, they get something called the activated energy. And when they get the activated energy, the reactant molecules now form something called complex molecule. Now, when they form this complex molecule, it helps them attain a certain high energy, and this energy helps them to be able to produce or be able to develop into products. And so that last energy where they should be able to get, or last transitional state they get before they produce the product, is what we call the activated complex. Is what we call the activated complex. Now, when they possess that energy, it makes them unstable, uncomfortable. And so the activated complex state is unstable because of its high energy content. Because it has a higher energy content, it makes it unstable. So what it does is some of the molecules decompose by losing energy. And so when the molecules decompose by losing energy, then it gives a stable product. And so when they decompose, then they give off a stable product. When they decompose, then they give off a stable product. So the activated complex state, it's an unstable because of its high energy content. Because of the high energy content that's attained, it becomes unstable. And therefore, the high energy molecules therefore decompose by losing energy. And when they lose energy, it gives or it produces what we call stable products. Basically, that's what it means. That's why when we are talking about in the first lesson, when I was talking about the products, the reactants and the products, I said that at the reactant stage, we are seeing that there's a loss. They are losing. Now, when they lose, then the product gains, or their loss help us to get to the product. And that's why in the reactant stage, we talk about the disappearance of A, disappearance of B. And now we come and talk about product formation or the appearance of C or D. Basically, that's what it means. So the difference normally between the energy of the reactant molecules and that of the activated complex is the activation energy. So the difference between the energy of the reactant molecules and that of the activated complex. And so the energy of the reactant energy and that of the difference between and that of the activating complex is what we call the activation energy. Activation energy. So let me just give you a sketch so that you see how it works. So for instance, if I have something like this, these are where the reactants are, these are where the products are. And so if the reactants are here, let's say A plus B, we are assume that they all have their energies. So these are the reactants of the energies of this. Now when they collide and they are able to get what you call the activation energy, so the whole of this constitutes that of the activation energy. Now they get to a certain point, that is the last stage. This stage is what we call the activated complex. Now when they get to it, and then they decompose. So when they decompose, then they either form what you call it, the product. They form the product. So the product will now be here. So let's say they come and form the C here. Now, so that is it. So yes, reactants, and here is product. Here is product, and the whole of this is the activation energy, and it is denoted by E small a, activation energy is denoted by E small a. E small a. And here is the activated complex. Here is the activated complex. Activated complex. So this one's activated complex. So that is it. So the stage, so the difference between the energies here and this one is the activation energy. So when you gain the activation energy, it helps you get to the activated complex. Then now we come and form the product. And so in instances whereby when we have to check or get the enthalpy change, when I say the enthalpy change, the change in the energies, that is, you know, enthalpy change will have to be changing. They have taught you enthalpy. So enthalpy change, that will be the difference in the energy of product, that of the product minus that of the reactant, unless my formula is wrong. So product minus reactant. Now, when it so happens that the enthalpy change is minus, is negative, then the reaction, we can see that this reaction is what? The chemical reaction is exothermic. When it is positive, then we say it's endo. We say it's what? Endothermic. Endothermic. And so if you are using this activation system, then what you are going to do is with the endothermic, this is exothermic. With the exothermic, the product will be down. And this here will be up. So that means here the product, indirectly here the product is higher than this thing. The reactant is higher than the product. So when the reactant is higher than the product, then that means you are going to get a negative answer. Now, on the other hand, if here is lesser and here is higher, if you have something like this compared to this, then that means here is higher than this. So when you do the subtraction, your enthalpy change or change in heat, change in energy, heat energy will be positive, and that you can see that this thing is endothermic. So that means endothermic. So you can say it is endo when it is positive. Let me just write for. So that is how I explain it. Now let's just explain. So using a collision theory I've explained, let us use it to explain the factors that affect rate of reaction. So the first factor we said is concentration. Now the collision theory states that for a reaction to occur, particles must collide. And so I've already explained. So for reactions, okay, particles must collide. Now the first one is the rate of collision is proportional to the concentration. So the rate at which the particles will collide will be proportional to the concentration. This means that if I have a bottle of water with the same volume of this thing and I put in more stones, the reaction of this thing, if I put in more stones and the stones that reach here, its reaction will be different from when I put in more stones to get to this point. And definitely, you know that when I put in more solute, which is maybe salt, when I put in more solute, the more I put in more solute, the more the concentration of this changes. That is it. So the rate of collision is proportional to the concentration. So increase in concentration of the solution or pressure of the gas means an increase in the number of molecules per unit volume. So when you increase the concentration, then that means you are going to increase the number of molecules per unit volume. So if I put in more solute, I'm increasing the number of molecules per unit volume, per this volume. So when the more I add more sugar, the more I increase the number of the molecules of the sugar per unit volume. That is it. So it increases the frequency of the molecular collision. So definitely there will be more collision because I'm introducing more molecules, and the number of collisions per unit time. and this increases the number of effective collisions, because the more I add more particles, it will definitely increase the number of effective collisions, and hence it will increase the rate of reaction. And so I've used the collision theory to explain how this thing occurs. So when you put in more solute, definitely you're increasing the number of molecules per unit volume, and as a result, it will increase the chemical reaction, because it will increase more collision. So we are going to get more effective collisions. So for instance, if I have if I want to, when I was explaining the effective collision, I said is the fraction of total collision of reacting molecule that produce chemical reaction. And so what I'm going to do is, if you have out of every 100, at least you can get some 10, which is good. But out of every 10, maybe you can get just one. And so comparing the 10 and the one, then you know that definitely if you increase the concentration, at least you can get more activated collisions. That can be the 10 I'm relating to. Basically, that is it. Now let's also talk about temperature. Now, when you increase the temperature increases the kinetic energy of the molecules. And you know, collision has to do with mobility, the ability of molecules. It was to be first, I said the ability of electrons to move. And so when you increase the temperature, it increases the kinetic energy. When we are saying kinetic energy is the energy possessed by a body by virtue of its motion. So when you increase its temperature, you increase the motion. So there is more collision. And as a result, when there's more collision, definitely it increases the number of collisions per second, and that's increasing the number of effective collisions. So with an increment in temperature, there will definitely be an increment in chemical reaction, rate of chemical reaction. That is it. Now let us also talk about surface area. Now you bear with me that if you are even cooking and you put the salt, the big ones, the rock salts, when you put it in water, the rate at which that salt will melt will be different from when you put the powdered salt in it. You realize that the powdered salt will dissolve much faster than that of the rock salt. And so the larger the surface area, because the powdered one has a larger surface area, and so the larger the surface area, it increases the collision per second, and hence help us to get effective collisions, and however contribute to a good chemical reaction. So the surface area also increases with increase in what do you call it? Rate of chemical reaction also changes with increment in the surface area. So when the surface area is fine, definitely you are going to get a good distance, or it increases the rate of chemical reaction. Now let's also talk about the catalyst. Now the catalyst, you know, doesn't take part of the reaction, but rather speeds up the reaction. And so in this case, the catalyst lowers the activation energy. Now when it lowers the activation energy, you know, and if we don't include any catalyst, then the product here would have to go through this path. But immediately we add the catalyst, it will cease it from moving through this path and just reduce the activation energy to maybe a certain level like this, because there's a catalyst there, so it wouldn't have to be moving all this way before it can listen. The catalyst will just speed up the reaction. So instead of moving to the activation energy, to rather decrease the activation energy. And when it decreases the activation energy, it hence increases the proportion of the molecules. So it increases the rate at which the molecules move with energy, and that energy will be greater or equal to the this energy that it would have traversed without, but for what they call it, the catalyst. And so instead of it going through, when we add this, it will just increase the proportion or the rate at which the proportion of the molecules with energy, and that energy will either be greater than the activation energy or be equal to this activation energy, and as a result, a product will be formed. And so when that happens, it also increases the effective collision, and thereby leading to what we call the increment in the rate of chemical reaction. So that is a little bit we can talk about. I don't want to talk too much about that. I've explained the rest. I've used the diagram to explain all these things. So when you are doing for an exothermic, an exo, always the product will be lesser than the reactants. So the product will come down, then the reactants will be up, using the same diagram. Now with the endo, the product will be higher and the reactant will be down, so that when you subtract, you can be able to get a positive. Because when the product is higher than this thing, then now you are going to get a positive. Basically, that's what it means. Now, I've explained all these things. Now let's do order of reaction. Sharp, 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 sharp. Order of reaction. Order of reaction. I hope I can please clean the board. I hope I can please clean the board. Can I please clean the board? If you mind me, I'll clean the board.
Yes,
It's Maureen on this platform. It's Maureen on this platform.
yes, sir.
Maureen.
Yes, sir.
Charlie, I miss you so much, yeah. I don't know. I'm bored with you, but I still miss you. Your face, Papa.
Oh, it's there.
Oh, don't look at me. Now where I'm bored with you, don't know. So the order of reaction. He said, when you here you support a better team, a team that they score 8-2. Which team is this?
Say.
Is this one to a team? Or this
So
one
you
is
like
not?
a day like that?
Or this one is not the Barca at Spain. Maybe this one is the Barca at maybe Kaneshi or Kolegono.
So you like a cream?
Now, if the money you used to buy the Barca jersey, use that to buy nose marks, the team is
Yeah, I'll go and buy. Because you said I'll go bunch.
go and buy it, use it to buy nose marks.
Say,
I learned Hannah too is a Chelsea fan. They scored them home and away 7. Why would I even worry myself to support Chelsea and Barca? These teams. Okay, so all work and no play, make that a boy. So let's continue. So the order of reaction. So given an equation for the reaction, XA plus YB is equal to product. The molecularity of the reaction is X plus Y. So that is it. But we are going to talk about something called the rate law or the rate equation. And the rate equation will help us to get the order of reaction and so on and so forth. Now, when we talk about the rate law or the rate equation, it's an equation that expresses the instantaneous reaction rate in terms of the concentration of the reactants taking part in the rate determining step reaction. So let me state it again. The rate law or the rate equation is an equation. So it is an equation. I'll teach you how to write it. It's an equation that expresses an instantaneous reaction rate. So it expresses an instantaneous reaction rate in terms of the concentration. So it expresses an instantaneous reaction rate in terms of the concentration of the reactants. So it expresses it in terms of the concentration of the reactants. And it takes into consideration the rate determining step reaction. So let me just give you an example. So for instance, if I'm giving MA plus so order of reaction. So if, for instance, if I have this reaction and I want to find for the rate of the reaction, this will be the rate. The rate of reaction R is given by the concentration of A. So first one, this case a constant because we are talking about a law here, the rate law or the distance. So this case a constant, the proportionality rate constant. So K, then A, then you come and raise this one to the power M. So let's raise the power M. Raise the power M times B, the concentration of B, raise the power N. So raise the power N. So that is it. In other words, if you can't see it well, let me write it well. So R, looking at the equation, so this will be like this. K is the proportionality constant, the rate constant. R is the rate of reaction. Raise the power M So R will be equal to K into bracket A raised to power M all over this thing. So, and this one is a rate determining step. This one is a rate determining step. When we get to rate determining step 2, I'll explain what it means. When we get to rate determining step 2, I'll explain it. So the rate law, this is the rate law. So R is equal to K, this A raised to power M, B raised to power N. So the unit of the reaction, that is R. The unit of this will definitely be this. They are in concentration, so this one will be mole per dm cube. So this is mole per dm cube. S minus 1. That is it. When we are doing the rates. Now, the A and B represent the concentrations of A and B. So this A and B represent the concentration of A and B. That is it. Now, the indices, the M and the N, are the orders of the reaction. So M and N are the orders of this reaction. Are the orders of the reaction. Are the orders of the reaction with respect to A and B. So the order of A is M and the order of B is N. Now the orders, we have the zero order. We have, to the one I was teaching myself, I said we have the zero order, we have the first order, we have the second order, we have the third order, and so on and so forth. At our level, we'll be considering the zero, the first order, and the second order. So the overall order, if you want to know the overall order of the equation, it will be this order plus this order. You know they are multiplying. When they are multiplying, you add the distance. So the overall order of this will be M plus N. M plus N will be the overall order. So for instance, if M is 0 and N is 1, then that means the overall order of the equation is 1. That will be 0 plus 1. Now if this is 1 and this is 2, then that means the overall order will be 3. I hope we're getting it. Now the order of the reaction is the sum of the powers to which the individual concentration of the reactant are raised in the rate law. And so the sum of this to which the individual concentrations are raised is what we call the order of the reaction. And so that is it. The order of the reaction with respect to a reactant indicates how the rate of the reaction depends on the changes in the concentration of that reaction. So basically that is it. Similarly, we are going to talk about the first order, the zero order, and the what do you call it, the second order. So if a reaction, now note this one, if in a reaction changing the concentration of one of the reactants does not affect the rate of the reaction, then the order of the reaction is 0. So for instance, if I change the concentration of this and it doesn't affect this rate, then that means the rate of this reaction or the order of this is 0. However, if I change this, if I double this, or if I double this and it also doubles this, then that means the rate of the reaction, the order of this one is order 2. However, if I also change this and it quadruples this, that means it increases this by 4 times, then that means it's in the second order. And so when I change this and it's what do you call it, it changes this, it doubles this reaction or this rate, then that means the order of this is the first order. Now when it quadruples this, then that means the order is the second order. Now if when I change this and it doesn't change anything, then that means the order of A is 0. So that one we call it zero order. When we advance, we are going to do a lot of questions and we'll understand it better. Someone should check the time for me. So similarly, for the first order, if the reactant concentration is tripled, the rate will also be tripled. So if in a reaction, changing the concentration of one of the reactants does not affect the rate of the reaction, then the order of reaction with respect to the reactant is 0. If the concentration of the reactant is doubled, while the concentration of the other reactant are kept constant, and the rate is doubled, the order of the reaction with respect to that reactant is 1. So if I change this and this one changes, then we are saying that this one is first order. So first order, then that means M is equal to 1. M is equal to 1. And so when we get it, we will solve some question. I'll explain it better. M is equal to 1. When I change this and this one quadruples, then N is equal to 2. So when we do some other calculation, now if the concentration of the reactant is doubled, so when I double this and this one intends quadruples or is increased by 4-fold, then the reaction is said to be in second order with respect to the reactant. Now, as we are considering this, we have to keep this one constant. When we are considering this, we have to keep this one constant. That is it. So the order of the reactions can only be found by experiment. So how we can find the order of reaction? We can find it by experiment and not deduced from stoichiometric equation. The order of the reaction M and N do not correspond to X and Y in above. So this guy, that is it. So the rate, now we can say that the rate is equal to rate, which is R, be equal to my K, which is A. Again, I've even written it. M. Now you bear with me that the order of the reaction is M plus N. That's the total, the overall order of reaction will be M plus N. The order of A is M, the order of N is N. Now R is the rate of reaction. K is the rate constant or the specific rate constant. So this K is the rate constant. So if you want to find this K will be equal to the rate of the reaction all over the concentration of this and this raised via powers. Do you get it, please? Do you get it, please? Now let's do rate determining step, RDS. When we finish, then we are done. Then we are going to solve a lot of questions to explain how it works. All the questions they can ask, so that any of them, if you see any of them, you won't be found wanting. Now the rate determining step. The rate determining step. If a reaction takes place in more than one step, that means if you have a reaction and it takes place in more than one step, the slowest of the reaction process is called the rate determining step. So if you have if your reaction takes place in more than one process or more than one step, the slowest of the reaction process is called the rate determining step. So the slowest of them is called the rate determining step. The slowest of them is called the rate determining step. The slowest of them is called the rate determining step. Hello, I hope you can hear. Please, can you all hear me? Can you all hear me? Hello, can you hear me?
Yes, sir.
Sorry, people are calling my distance. They are calling on my line. My line, I'm using it for the Wi-Fi. So when they call, it cuts the distance. They are calling from school. McGee. So Walker is calling. I want to teach first. So please. So that is it. So if a reaction takes place in more than one step, the slowest of the reaction process is called the rate determining step. So the slowest of them is called the rate determining step. Now, the slowest step or the rate determining step can be used to find the order of the reaction. And so the rate determining step can be used to find for the order of the reaction we are talking about. The coefficient of the reactant to that step can be used to find the order of the reaction. And we can also use the coefficients like we did. If you are given 2, Maureen, stop that. Maureen, stop that. So if you are given 2A plus if you are given 2A plus 3B, these are the coefficients. So we can use the coefficient to find for the order of the reaction, just as we did. So this one will be the A raised to the power 2, just as we did in our previous lesson. So we can use that to do it. So the coefficient of the reactants of that step can be used to find for the order of the reaction. Now the rate determining step for the reaction, this, you've already said it. So we can use all that to do it. So what a plus, when I give it a plus 2d, so this one we are giving something like this, 2a plus 3b. So it's giving us it's giving us 3c. Now, and the whole of this is also giving us a plus 2b, a plus 2b will give us d. Now they said we should find for the rate determining step. The chemical reaction, when I read the rate determining step, I said that if the reaction takes place in more than one step, so you realize that the reaction is taking place in more than one step. Now, always the last one is the slowest step. So from here you go here, from here you go here. I would have from here you get. That means when this one gives you this, this will come and give you this, and that will give us d. So this will be the last step. So if you have to find for the order of reaction, you are going to use the coefficient. Here is 1. The coefficient of this is 1 and 2. So the coefficient, the order of reaction will be 1 plus 2, and that will give us 3. The order of reaction, we use that of the reactants, please. We don't use the product, we use that of the reactants. So that's why I consider only the reactants. So this is 1 plus 2. So the overall order of reaction is 3. Looking at this. Now, so there's a difference between the rate of reaction and that of the constants. So when you're asked to distinguish between the rate of chemical reaction and a specific rate constant for the reaction, you are seeing that the rate of the chemical reaction is the amount of reactant consumed per unit time. And so when you have to distinguish between the rate of reaction and the specific rate constant, the specific rate constant is the K. The rate of the reaction is the R. Now the rate of the reaction right from onset, we say that is the rate at which, or is the amount of reactant consumed per unit time. So we say that. Now the rate constant is the proportionality constant, which is the K, is the proportionality constant in the rate law at a given temperature. And so the K in it is a proportionality constant in the rate law at a given temperature. That is it. So that is it. So we have a lot of work to do. We have just 6 minutes to go. We have just 6 minutes to go. I want to see if I can get some questions so that we can. Good. So okay, let's do this question. Let's do this. If you can't even finish, at least I've done teaching this. So anytime we meet, we can solve questions. Then we continue. Okay. So when you are given something like this, x plus y. X plus y. There's a question. X plus y plus z is equal to Q plus P. Q plus P. The rate law was found to be. So the rate law was found to be. This is the rate law we are given. Okay. I let my manual is finished. So don't worry. When it cuts, then my manual is finished. We'll continue next time. So the rate is given by K X Y